In this lesson, we're going to start examining three-dimensional geometry. So one of the ways we identify the difference between two-dimensional and three-dimensional, we use the notations R2 and R3. R2 stands for there's two real numbers that make up each point. So in here, we're thinking about the XY plane. So 2, 3 would be 2 for X and 3 for Y. Okay. To describe vectors in two-dimensional is easy. You talk about your horizontal and your vertical, and you got your vector. We call these the components. Okay. So if we look at a diagram for a second in R2, two-dimensional, okay, OP stands for a vector that begins at the origin. We always use O for origin. And the tip is at P, which has the coordinates A and B. Anytime we talk about a vector at the origin, we call that a position vector. And we can move position vectors around in space. This leads us to what we call our first vector form, component form. OP is made up of the components A, your X direction, plus B, your Y direction. Or in other words, oops, I made it a little bit big there, I guess. It makes your vector addition, or OP. In this case, OP has the components 3 and, 2.5. I guess 2.25 there. And we call that a position vector. This would be my X. This would be my Y, or my horizontal and vertical components. I do want to point out there's a difference between these two things. The first one, the green one, is a vector. The red one is a point. So be careful with notations. If you're talking about a vector, you have a vector symbol above it to say, hey, this is a vector that joins the origin to point P, as opposed to the discussion of just being a point. Okay, that's what R2 looks like, two-dimensional, just a horizontal and a vertical direction. R3 is what we're going to discover today. So our big idea is to investigate three-dimensional space. Okay, there is a handout that goes with this. I put it up on Edsby, so you guys can take a look if you need to. I'm going to do the handout with you in this video so you can understand how this works. But basically, it's the idea of our classroom where our front of our corner of our room is going to be our starting point. We're going to have a front wall, a left wall, and a floor in this diagram. Okay, so same diagram, same idea, just the handle that goes with it. Okay. Because we now have a three-dimensional classroom, we're going to need three coordinate axes. Notice in this diagram that we have an axis that runs along the intersection of the floor and the left wall. That would be, I can draw on here, that would be this axis right here, which we're going to call the x-axis. Okay. There's an axis that runs along the intersection of the floor and the front wall. So along the back, the floor and the front wall, we're going to call that the y-axis. And which axis runs along the front wall and the left wall? That vertical one, we call this the z-axis. What point does the front left corner of the room represent? We're going to think of this always as our origin. So we're going to call that 0, 0, 0, or the origin, or in vector format, the letter O, our starting point. Notice I have three numbers now because we have three different directions. Okay. What angle do the three axes make with each other? Here's where it gets a little bit of thinking involved. These are all right angles, even if they don't look like it. That's a right angle. This is a right angle, and that's actually a right angle. That's on the floor. So you're going to have to start thinking three-dimensional a little bit to think about how these are going to be connected together. Okay, the three coordinate axes taken in pairs determine the three planes, called the coordinate planes. A plane is a two-dimensional surface. Think of it like a piece of paper. For example, the xy plane is the plane that contains the x and y axes, hence the xy plane. Which plane do these represent? So if I think about the floor itself, the floor is made up of the x-axis, and it's got that or that, so the y-axis. So the floor is called the xy plane. Okay, the front wall. The front wall is made up of, still got the y, but now we've got the vertical part, so that's a z. That front wall would be the y z plane. And the left wall, obviously that's going to be our x z plane. And because it's made up of the x and the z. Question 3 here. Points in 3 space, called R3, are represented by an ordered triple of real numbers, x, y, z, alphabetical order. Make it easy for ourselves. So locate the point x, y, z, start at the origin, so that's the front left corner of the room, move x along the x, then y, that would be your left-right parts, so parallel to the y-axis, then z, which would be your up-down parts. We're going to try and figure out some of these parts of the room. So we'll start with the 8 corners of the room. So if we want to think about this point right here, that's one point of the room. Well, we can start with this one, I guess. 0, 0, 0. To find the next one, we have to come out from there. 1 spot, 2, 3, 4, 5, 6, 7, 8, 9, 10. Point out to you guys in case you missed it, 10 units. The x-axis is 10. I didn't move left or right at all, so nothing on the y. And I didn't move up or down at all, so nothing on the z. That point is 10, 0, 0. If I think about another easy point, this one, okay, I'm just moving across the wall. So I had to move 1, 2, 3, 4, 5, 6, 7, 8. It does say in the question it's 8 meters, but just in case, that's where the 8's coming from. Okay, because I didn't come out from the wall, I'm at 0 on the x, 8 on the y, and 0 on the z. And the other really easy one, probably the one at the top up here. Okay, I didn't go on the x-axis at all, or the y, but I went up 1, 2, 3, 4. It does say 4. So 4 meters up. Those are the super obvious ones. Let's try ones that aren't quite as obvious. Let's do this guy. So that's out 10 on the x. I'm going to go this way. I'm going to go across on the y over here. So out 10 over 8. That makes this point 10, 8, and 0. If I think about, I got all the floor points, it looks like. How about this point up here? I have to come out the x, 10, then go up the z, 4. So 10, 0, 4. Yeah, I've got one over here. So this one has no x's, but if I go across the y, then up the z, no x's, 8 on the y, and 4 on the z. And there's one more point, it's kind of hard to see. It's right here. It kind of looks like it's in the middle of the room, but really that's like the back corner of the room. To get there, come out the x, go across the y, then up the z, and this point right here, it's kind of hard to see, 10 on the x, 8 on the y, and 4 on the z. And there's the 8 corners of our room. Okay, find the center of the room. Well, again, kind of hard to tell, but the center of the room, on the floor is kind of easy to tell. The center of the room on the floor is here, but I also need to bring it upward. So I got to think to myself, vertically above the floor, it's somewhere around there. So how can I find that spot? Well, if the room is 10 big and 8 wide and 4 tall, the center of the room would be half of all of those numbers. So how about 5, 4, and 2 as the center of our room? That would make sense. And the top left corner of the blackboard. That one's on the wall. Top left corner, right there. So I didn't come out from the wall at all, so no X's. On the Y's, I have to go over, I don't know, what's that, like 1.5? And then up 1, 2.5. So I'm thinking, how about 0, 1.5, 2.5? And I literally just counted the boxes that time. Probably a little more than halves, or a little bit less than halves, depending on what you're talking about, but you can estimate. Okay, the top of the teacher's head. Okay, the teacher's head. She's kind of in the middle of the room, not quite in the middle of the room. She's right about there. Okay, notice she's not against the wall. Her chair looks like it's out from the wall 2 boxes. That's your X part. It looks like she's away from the wall 1, 2, 3 from the Y part. And then we kind of have to estimate how tall she is, because again, she's not against the wall. If I were to draw a line about how tall she is and then think of that line being like, I don't know, over you, ooh, I can't do that. Let's not do that. Against the wall there, how tall is that? I'm going to guess, I don't know, like maybe a box and a half. Again, we have to estimate a little bit. So I'm thinking for the teacher's head, she was out 2 from the wall. She was across the y-axis 3, and her head is up about 1.5. Okay, estimating in 3 dimensions is pretty hard when you're using 2-dimensional paper, or in this case, 2-dimensional file. We can do our best. Okay. The 3 coordinate planes divide 3 space into regions called octants. The octant where X, Y, and Z are all positive is called the first octant. That would be like our classroom, thinking about the front left corner as being 0, 0, 0. From the diagram, try to visualize the other 7 octants and the rooms situated in each of these. So think about our classroom, if you will, as this being our classroom. Can you picture where the other 7 octants are? Okay. So, well, one of them would be behind the blackboard on the other side of the wall. One of them would be behind the left wall, kind of think of like the hallway, if you will, but as a classroom. And then there's one in the corner of those things, kind of like back here, right? It'd be in the hallway and behind our front wall. That's what those would be. So how many, what was our question? How many of these rooms are located on the same floor? There's 4, or 3 other ones, but there are 4 things that are on that floor of octants. Okay? So if we're describing them, let's draw them out, if you will. Here's, I'm going to draw this. Make that too big. Eraser. Come on, eraser. Okay, here's our classroom. This is classroom number 1. Okay, it's got X, Y, and Z all being positives. If you think of this as being the wall, our front wall that the smartboard's on, there's another room behind it. Well, those values for X are negative X's and Y's and Z, because instead of coming out the X-axis, you've gone backwards on the X-axis. Okay. On our left walls as being this wall, there would be another one over here. And to get there, our X's are positive, but our Y's are negative because the Y-axis goes this way. So now we're negative Y's, and these would be the Z's. Okay. There would also be a classroom back here in this spot. Here you'd have backwards on the X-axis, backwards on the Y-axis, and still on the same floor, so Z-axis. those would be all the rooms attached to our room, if you will, where this is the origin. Okay. Part B says how many rooms are located on a different floor? Well, the octants, if you think about the z-axis being, here's our z-axis here. Here's our z-axis going up. You could also go down on the z-axis. Think about the floor below us. If we did that, we would have, again, 4 rooms. The one directly below us would be x, y, and have negative z's. It still has the same floor as us, but it's below us. 3-dimensional means we've gone down the z. The one behind that would be negative x and y and negative z. The negative, these have gone down a floor, and x, you're going backwards on the x-axis. The one beside it would be x and negative y, negative, and negative z. And of course, you can have this one back here, which has negative x's, negative y's, and negative z's. And those would be the room sort of in the hallway, below us, and over one. Okay. It asks us, what corner point do they all share in common? We can figure that out. That would be our origin, of course, 0, 0, 0. That's part C. And this is part B. This was A. Okay. Next part asks us, what are the y and z coordinates of every point on the x-axis? Let's go back to our picture for a second here. Way back here. I'm going to erase some of the stuff so we can see a little bit better. Go away, go away, go away. Okay, if we just thought about the x-axis itself, which is the left-hand wall, and I thought about my y's and my my y and my z values along there. So here's my x-axis right there. Okay. This point we said earlier was 10, 0, and 0. As long as I'm on the x-axis, and it could be forward on the x-axis, or if I went back into the classroom behind it, backwards on the x-axis, I have an x value, but my y value is always 0, and my z value is always 0. As long as you're on the x-axis, all you have are x values. Okay, so you have x, 0, and 0. What if you're on the y-axis? Well, similarly, you won't have any x values. You have a y, but no z. If you're on the z-axis, you'll have no x's or y's. You'll just be going up or down, so you have a z values. If you think about this in terms of the planes, the xy plane, we said earlier, was the floor. So thinking about this, my floor is right here. If I'm on the floor, my z value is always 0. I don't get a z value until I get up off the floor or go down through the floor. So if I'm on the xy plane, z is 0. If I'm on the xz plane, that's your left wall, the y value has to be 0. And if we're on the yz plane, that's the front wall, the x value is 0. If you're on the front wall, you haven't come out from the front wall, you're literally on it still. Okay, number 7, what condition is satisfied by every point on the plane that contains the back wall? So what do I know about the back wall? The back wall is made up of a y value, because I have to go left or right on it. It's made up of a z value, because I'm going up or down on it. But to get to that back wall, which is in our picture, right here, every x value has to be that far from the front. Doesn't matter where I am on that wall. I'm always the same distance from the front. So no matter what, x has to be 10. So every point on here is going to be 10, and some y, and some z. If we're on the ceiling, I could have any x that I want to. I could have any y that I want to, but z has to be 4, because every point on the ceiling is 4 units up from the floor. No matter where I am on the ceiling, I'm 4 up from the floor, 4 up from the floor, 4 up from the floor. And the last one, of course, so I'm on the right-hand wall. Well, that means I'm 8 units over from the left-hand wall, which is my y value. So I have some sort of x, 8 from the right wall, sorry, left wall, and I'm up or down on that wall somewhere. And y has to be 8. Okay, last but not least, going back to our idea of components again, let's say we draw a vector from the origin to the point 10, 8, 4, which is the point on the ceiling furthest from the origin. So in our room, where is that? Let's get rid of some stuff again here. I'm going from the origin, that's right here, to the furthest possible point from there, which in the picture is actually right there. Doesn't look very far, but you're having to think three-dimensionally in our classroom. The bottom left corner of our room to the back right corner of our room. And what does it want me to find here? It wants me to find the length, the magnitude, the size of OP. How do we do that? To do that, we have to think about what vectors were added together to get there. To get there, we actually had to add this vector plus this vector, plus this vector plus this vector. And if I do that, it connects the green one. So the question is, how do I find the size of that vector? I can do that by cheating a little bit and finding the size of this vector plus this vector. Because those two combine to make the green one. And I think to myself, hey, this is a right angle triangle on the floor with my A, my B, here's my right angle, so the purple one's actually the C. So I can use some Pythagoras here and say to myself, okay, on the floor and against the floor, I've got 10 squared plus 8 squared equals C squared. That's the diagonal across the floor of our room. That's 164 for C squared. But I want C, so we're going to have the square root of 164. And it's going to leave it exact because I don't really want the decimals. It's 164. And then if I think to myself, hey, I want actually the up and down one. The up and down one is itself a right angle triangle. Hard to see, but there's your right angle. This is the triangle. If we draw that, it's going to look like this. Oops. Draw it. And this was the origin. This was the back corner of our room right here. And we just figured out that the distance was 164, the square root of that. We know the height of the room up and down was 4 meters. So can I find this C? Sure I can. It's a right angle triangle again. So I've got the square root of 164 squared plus 4 squared equals C squared. Which is what, 180? Notice the squared and square root, these two things just cancel each other out this way, and this guy's cancel. So we've got 164 plus 16 is C squared. In other words, C is the square root of 180, whatever that comes out to. Can I also point out that this 164 root actually came from doing this? Or in other words, if I want to find the size of a vector in three-dimensional, I could really do my x component squared plus my y component squared plus my z component, and that will give me the size of my vector. And because technically it's squared, and to get rid of a squared I square root, there's how we can find the magnitude of any vector in 3 space. If you add all that together, you should get the square root of 180. So it saves me from doing Pythagoras twice. Okay, that's our investigation. Just to summarize just for a second here. Okay, in R3, the origin is always going to be the front left corner of our room. We call this 0, 0, 0. The positive x-axis comes towards us from there. The positive y-axis goes out to the right from there, and the z-axis always goes up. So they use what they call the gun. So if you make a picture of a gun with your hand and then turn it towards yourself, your finger, your first finger, should be pointing in the x direction. And your other fingers, if you point them out, point in the y direction, and your thumb points in the z direction. We call it the gun. It's an easy way of thinking about 3 dimensionals. And in each point in R3, you should have 3 components: the x direction, the y direction, the z direction. If we're talking about a point, we call it the letter P. If we're talking about a vector, we use vector notation. We're going to try and draw some of these points. They're a little bit tricky because you have to kind of think 3-dimensionally. We'll give it a try. Okay, so we're going to draw our axis. Z's up and down. Y goes across, kind of where the x used to be. X is going to come towards us. And you can think to yourself, really, there's lines that are like kind of like diagonal across here. And they go into the negatives if you want to, if that helps. Okay, and there's also lines that go across. And there's lines that go back that way and this way. You can draw as many lines as you want to, but you kind of have to start thinking 3-dimensionally. Okay, 1, 2, 3 means I have to come out 1 on the x, so I'm coming out here, and then 2 on the y, so I'm going to cross 2. And here's the hard part, I have to go up 3. So here's where you have to imagine to yourself that I'm going up 3 a little bit. So up 3 would be about there. That's point A. B, -2 on the x means I'm going backwards on the x-axis. So if the origin is right here, backwards on the x-axis means I'm going back 2. I'm going 1 on the y, and then I'm going to go 1 on the z, so I'm going to go up. The hard part is the up part. Okay, you have to imagine that's physically above the xy plane, above the floor. Okay, we'll try C. It's 1 on the x, so 1 towards us. -2 on the y, so we can go left on the y-axis. 2 spots. And then 1 up on the z. You notice I try to make my ups about the same size. That would be C. D is 1 on the x, -1 on the y's, and 1 on the z's. So I'd say D is about there. And E, 0 on the x, -1 on the y, so backwards on the y, and down on the z. I'd say E is about there. That's below the xy plane. Hard to tell. It's like to think about this. You kind of have to start thinking, that would be like below our floor, right? That's what's happening there. It'd be out in the hallway and below our floor. Okay, that's our 3-dimensional ideas today. We're going to have some questions we're going to try. There's a whole bunch in there. Just there's good thinking questions. Get our brains warmed up in 3 dimensions. Give them a try. If you're stuck, come see me or send me questions, and I will help you through it.